All right. Okay. Hi, everyone. Strange days. It's you know, for those who are in class, I hope that's the right thing for you. For those who aren't, it's great. And if you're watching this later, that's totally fine. It's a hard time. I do love being part of the boating community. I hope that all of you have people you feel like you can talk to. If not, there's tons of adults on this campus who care about you sort of like more than is rational or necessary. So you have people to talk to. You can come talk to me. It's a little weird. I remember teaching the day after the 2016 election, which was a different strange vibe. And you know, there were students like crying in class and stuff. And I said, look, I know it's weird. I'm a professor, but I am from the South and we were huggers. So if anybody needs a hug or anything, and then people came up after class, boys and girls came up to class like hugging me and stuff. I wasn't expecting like to get like 5 hugs, but and now it's a pandemic, so I don't even know if that's. But anyways, the point is, if you need support, if you need someone to talk to, my door is always open. I'm happy to talk about anything. And otherwise, I hope you have lots of good support. But yeah, okay. And so you all saw my email yesterday about flexibility, and so the official deadline of the test is tomorrow night. The test write-ups is tomorrow night. We'll keep pushing it back, but then again, if you need more time, you can take till Friday. And if you need more time than that, just let me know. We can talk. And there's a problem set for Friday that's on geometric series, so it's material we've already covered. Okay, so then today, I want to talk about series tests. We sort of started this a little bit last time, started analyzing series. Let me just show this handout. So on the handout page, I'm going to kind of end up going through this series tests one handout. So I'll leave it on screen here, but if you're watching at home or later, you should. It's a good idea to maybe download this because I'll be referring to it. And so, yeah, so I'll just keep it on screen because I want to go through these tests, try to explain where they come from, and give you some examples. And then the second page of the handout has a bunch of practice problems, but maybe we'll just kind of talk through some of them together today. We'll take a break and then come back and talk through some of the examples. Okay, so a video I had posted, but then I sort of made optional, was about this first one, the test for divergence. So well, actually, before I even get to that, let's just say this is like series tests. I guess that's what the handout's called, series tests. And I've made this point that like it's actually very, very difficult to sum. Even if we know a series converges, it's difficult to find the number. So usually we'll just ask, I'll give you a series and we'll ask, does this converge or diverge? Okay, so series tests. It's for convergence and divergence. All right, and then so we've already seen, one that we've seen is the p-test that we sort of developed last class, which was that, and it's very much like the p-test for improper integrals. That this guy, if we look at like this, like the harmonic series is when p equals 1. The 1 over n squared series, which is that one that converges to pi squared over 6, is when p equals 2. That this converges for p greater than 1, and it diverges for p less than or equal to 1. And we said we could basically compare this sum to the improper integral. We were actually able to see like in the picture, right? That's what we did last time. that we could actually do it by comparing, like justify this by comparing to the area under the improper integral, the related improper integral. The next one, so this is a test just to, at some point it's like you want to have all these tests in your back pocket and think about which ones could apply to which situations. So the next one is what I call the test for divergence. And actually, this should be the first test you do anytime you see a series. So let me start with an example. Let's do the sum n equals 1 to infinity of 5n minus 3 over 100n plus 1. Something like this. Okay. You can write, by the way, anytime you see a series, the first thing you might want to do is just start writing out some terms. Like, it doesn't hurt. This looks like an abstract thing, so let's just start plugging in. If we plug in 1, we get 2 over 101. Is that right? If we plug in 2 for n, 7 over 201. Math 12 over 301. And actually, I guess we're just adding 5 on top, right? 17 over 401, 22 over 501, etc. And you might ask yourself, you start writing out terms of this, and you might think, okay, does this converge? Does this diverge? What's going on? Well, what happens when n gets large? That's maybe the first thing to ask yourself is, we call this thing a sub n, sort of the individual terms of the series. And just remember, we're adding things together. So what happens as n gets large? So what I mean is, let's take the limit as n goes to infinity of a sub n, which here means the limit as n goes to infinity of 5n minus 3 over 100n plus 1. What's going to be the limit when we do that? Or how do I resolve this? Right now it's infinity over infinity. So there's a couple ways to resolve this. How could you resolve this? If I want to figure out this limit. Try to watch the chat also in case people have questions. Someone tell me, if I gave you this limit, how would you resolve it? We could do L'Hopital, right? If you differentiate so it's infinity, it is an infinity over infinity. If you differentiate the numerator, you get, somebody say it. 5. If you differentiate the denominator, you get 100. So it's actually 5 over 100. It's 1 over 20. A way I like to do this same problem is, there's another way you can do this, which is divide the top and bottom by n, because there's an n right here. So if I multiply by 1 over n, then really what this becomes is the limit, because I can do that because that's 1, right? I'm just multiplying by 1 in a strange form. This becomes 5 minus 3 over n over 100 plus 1 over n. And now that's nice because now as n gets large, we force the infinities in the denominators. And so things go to 0. So this is just 5 over 100, which is 1 over 20. Okay, so that's the terms of the series are going to 1 over 20. But let's think about what that means. Yeah, what does that mean? We're going to be adding 1/20th every time, basically 1/20th every time. And it's sort of, you can sort of see it getting there, maybe. Wait, am I doing math right? Maybe. Yeah, I guess so. I mean, yeah. So here, like I'm adding in dot, 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 but I could basically add at some point just say I'm really adding 1/20th over and over again. So maybe one way to say this is the sum from 1 to infinity, 5n minus 3 over 100n plus 1 is approximately, like, I can start the same way, 2 over 101 plus 7 over 201 plus 12 over 301. But then if we go down, you know, a few hundred terms, we're basically adding 1 over 20 plus 1 over 20 plus 1 over 20 forever. So that's why I put approximately here, because it's not exactly, but we could just basically think of the integral, I mean, the series as doing this, right? I have to be careful when I say infinite series, because sometimes my iPhone thinks I'm asking for Siri. Some of the videos I recorded about infinite series, I'd be like recording all of a sudden, I'd be like, yes, can I help you? Like, what? Oh, I said the word series. Hey, series. I was waiting to hear if there was a, if it responded. Well, there's nothing called the Hey series. Might be actually. Anyways, so, but can you think about what's going to happen now if we're just adding 1/20th over and over again? We talked about something similar like this with the harmonic series where we're adding half over and over again. It's going to diverge, right? You're basically, I don't know how you guys like to conceptualize addition, but for me, it's the number line. I always see things moving along the number line. Like if I'm adding things, I'm just like, if I add 5, I just move over 5 units on the number line. So here you're moving over 1/20th on the number line. You're basically making these equivalent hops on the number line, but you're going to do that forever. And so you're going to hop your way off to infinity. Does that make sense to everyone? So this has to diverge. It's hopping off to infinity. Right, and so that's actually a big point here, is that if the individual terms are not going to 0, if those aren't trending towards 0, then it's impossible for the series to converge. Basically, if a series is going to converge, you're asking for an infinite sum to slow down and stop. It's only going to slow down and stop. It only has a chance of slowing down and stopping if, or coming to a complete stop. A lot of them slow down, I guess. It only has a chance of coming to a complete stop if you're adding less and less over time, and you're basically adding 0 when n gets large, right? So that's actually kind of what the test for divergence says. So the test for divergence officially is, and it's up on the screen there, I think, too, or it's on the handout. So given an infinite series in general, like this, if the a sub n's don't trend towards 0, so if the limit as n goes to infinity of a sub n is not 0, then the infinite sum must diverge. Okay. And so this is why I say this is the first thing you should check every time you encounter an infinite series, because it's kind of the simplest test you can apply. Just like make sure the terms are going to 0. Notice that so in math, well, there's logical equivalence statements. So there's 2 different types of, this is something you learn sort of properly in math reasoning, but this is a statement of the form, if P then Q, right? There is something called the contrapositive. actually there's two different things. There's the contrapositive, which is if not Q, then not P. Now this is actually logically equivalent. Like, I usually have examples of this in my head. Something about, I don't know. I had this thing with when I was taking out my trash every week, Wednesday night, Thursday morning, that like, it seems to always be raining and gross. So then my trash cans are always like gross and filled with water in the morning when I go pick them up. So it's like, if it's Wednesday, then it's raining. If it's Wednesday night, then it's raining. So if it's not raining, then what can you conclude? It's not Wednesday night, right? So that's logically equivalent. But there's also the converse, the logical converse, which is if Q, then P, where you just switch the order. And so I said, if it's Wednesday night, then it's raining. If it's raining, does that mean it's necessarily Wednesday night? No, right? It could be raining some other times. So this is not always the same. The contrapositive is logically equivalent to the original statement. And we can write, I want to write this down here. So this would be if the series converges. Because that's the negation of this. Not, when I say not, I mean like the negation. Then, well, the negation of not being zero is being zero, right? Then the limit as n goes to infinity of a sub n must equal 0. So these are sort of logically equivalent statements. Okay, but the converse is if the limit of as n goes to infinity of a sub n equals 0, then the series converges. Wait, that's not, what did I do? No, if it diverges. Wait, hold on. Actually, what I'm doing is the contrapositive of the converse. That's bad. So the converse really is if the series diverges. Sorry, because that's our Q, right? This is our P and this is our Q. So if the series diverges, then the limit as n goes to infinity of a sub n is not 0. And I guess I could have the contrapositive of the converse, which is if not if not P, then not Q. Yeah, that's another way to talk about the converse, is you just negate both of these. If not P, then not Q. So what would that say? That would say if the terms go to 0, then the series converges. You can sort of do this with any mathematical statement. Most mathematical statements, a lot of mathematical statements are the form of implication, like if then statements. And so it's kind of interesting to try to analyze all 4 of the possibilities you get. Oops. So these are also equivalent statements. But is it true? Is it true that if the series diverges, the terms must not go to 0? Or if the terms go to 0, the series must converge? The answer is on the board near the top. What happens to 1 over n to the p as n gets large? Goes to 0, right? But that doesn't guarantee convergence. So we have to be careful that these are false. These are not true statements. It's actually very much like the last question on the test that was about if the function goes to 0, must the improper integral converge? And the answer was false there too. So this is false. For example, the harmonic series. That should just be the one you keep in your head. The individual terms of the harmonic series go to 0, but the series itself diverges. So it's coming, so again, hopping along the number line, it is slowing down, but somehow it's still like, doesn't hit the brakes fast enough and slides off to infinity. It's strange, but it's important to keep this. But these ones up here are true. These are true. This is what the test for divergence says. So okay. And so that's what I'm saying. So like in that example up there, because the terms weren't going to 0, the series had to diverge. Okay. Any questions about that? Does that make sense? There are some examples. There's more examples on the next page, but I kind of want us to look at the problems on the next page after we've stated all these tests, so then we can try to decide which one to use, which test to use. I think that's always the question. It's like when you're faced with an integral, it's like, do I integrate by substitution, by parts, trig substitution? Kind of the same thing when I see a series, which test is most appropriate, But you should always check this. You should always think about this, because that's always, it's game over if you find the terms don't go to 0. Actually, I'll go give you one more example that I don't think is on the next page, but it's kind of famous. So so another one that's kind of famous is if I just had, I feel like we might have seen this. I can't remember if it was on a problem from the homework or something, but I feel like it came up. Which is the series, the sum of sine of n, sine of n. I just did something like that. By the way, I don't have to start at n equals 1. I could start at n equals 0 or n equals 5 or whatever. It's just what matters is it's going off to infinity. So this is sine of 1 plus sine of 2 plus sine of 3 plus so on. The issue here is that radians are weird. 1 radian is a weird angle. So it's just somewhere on the graph of sine, right? Sine of 2 is some point between -1 and 1. But what happens to sine as n goes to sine of n as n goes to infinity? Oscillates forever, right? So the limit actually just doesn't even exist. The limit as n goes to infinity of sine n does not exist, because the sine curve oscillates forever. You have to be a little careful, because if I did something like sine of n pi instead of sine of n, sine at multiples of pi is always 0. So I could be tricky and be like, oh, actually it's just 0 plus 0 plus 0, which does converge. But here, because these are weird angles and they kind of, it's really random, it's hard to predict where they're going to be on the curve. Because the sine, yeah, so this doesn't exist. Therefore, people seen this little triangle for therefore? No, sorry, this is a way some people write therefore. There's all these symbols in math. And sometimes I use them, sometimes I don't. Therefore, this infinite series diverges. Because as you go on forever, it's just kind of moving around a little bit forever. It's hopping down the number line, but it's just hopping forward, backward a little bit here and there. It's in a kind of chaotic way. that believable? Any questions about any of that so far? That was really the video I was going to ask you to watch, but some of you did watch, so you're probably bored. Although I don't think I talked quite about all of this stuff, but okay. Let me come back to the limit comparison test just because that one's a little stranger, but if you go down the handout, there are two more tests, direct comparison and the integral test, which I claim that we've already sort of seen both of these in different forms. So let me talk about comparison tests. Actually, I guess maybe I'll talk about the two comparison tests and then. So one is direct comparison, and this is just like we did with improper integrals. It's the same exact idea. We used to compare improper integrals. So like, for example, now if I had something like the sum of n plus or n minus 3 over n cubed plus 4n plus 7. I mean, just pretend you turn it to an integral and turn the n to x's and write a dx. It's almost the exact kind of thing we've thought about before. That what we can do is we can sandwich this. Actually, what I really should do is do a simpler example. Let's just do n. It's a little easier if they're simpler. Let's just do n. Okay, now the idea, remember the idea is that like, as n gets large, the n cubed down here dominates the 4n plus 7. So we can pretend like those aren't there. So this should behave like n over n squared. I'm sorry, n over n cubed, which equals 1 over n squared. So it's like a p test n equals 2 converges. So there's the informal n cubed plus 4n plus 7 is really just like n cubed when n is large. The lower terms are negligible. So n over n cubed plus 4n plus 7 is less than, I'm sorry, what am I saying? Is just like, I started to do the comparison, 1 over n squared. So the summation, so this is like the sum of 1 over n squared, which converges. That's the p test of p equals 2. So right, we've done this exact kind of argument before. It's just with integrals instead of sums, right? And then the more formal way to do it is to actually sandwich this between things, or like maybe sandwich the bottom between two multiples of n cubed, and then flip over, multiply by n to build this expression. And this should seem very familiar. In fact, I think you were writing it up, an example like this for the write-up. It's like, what is it, 2D on the test. So, so the more formal, which I want you to do, to be able to do, it's nice to give the informal because you can sort of tell what's going to happen, but then if you want to justify it really, you're supposed to give this formal argument. So more formally, that we could put n cubed plus 4n plus 7 between, say, like 10 n cubed and 1/10 n cubed. You can sort of check, make sure, but probably that's true. right? That's the bottom, that's the most complicated term. And then I want to build the expression inside the series. So if we flip everything over, so this is actually gonna be less than that flipped over because the inequality is reversed, right? I'm not sure why I'm saying less than or equal to, I probably could just say less than. So that's less than 10 over n cubed. That's greater than 1/10 times 1 over n cubed. Just because the inequalities all reverse. Right. Then I can multiply through by n. And it gets to be kind of tedious because you've done it before. And then because this sort of says that each individual term is between two terms, so then let's just add them all up. We can now sum. So that implies 1/10 the sum of 1 over n squared is less than the sum of n over n cubed plus 4n plus 7 is less than 10 times the sum of 1 over n squared. Right, and so now we've sandwiched our series between two series that both converge. Sorry, I feel like we're treading familiar ground, so I'm going kind of fast through it. This converges. So this also converges. Right. Yeah. Familiar? Okay. So that's sort of direct comparison. It's exactly like direct comparison in proper integrals. Okay, so the way it was stated up there is kind of the way the book states it. But I've sort of done it this way where you could just get the inequality on one side. Like this is sort of saying the sum of a, and the way it says on the handout, if you read the direct comparison part of the handout, it says, you can kind of just build the inequality on one side if you want. I always like to build it on both sides just because it's like, or if I can, I guess there's some examples where maybe you can't, but let me share screen just to make sure people see this. So yeah, so you're given some series that you don't necessarily know how it behaves. But if you can compare it to some series that's bigger, but that series converges, then the series that you're examining also has to converge because it's less than something finite, so it also has to be finite. On the other hand, if you can make the questionable series bigger than some known series that diverges, then that series also has to diverge. So there are times where maybe you just do I can actually think of an example of a direct comparison that might require, yeah, actually, let me give you an example. Actually, I think this is on the back of the handout, but that's one of the classic examples. So I'm not really, I can't really come with others. So let's do this. The sum as n goes, I said 2 to infinity just because natural log of 1 is 0, so that term wouldn't matter. But natural log of n divided by n. It turns out this will also satisfy the integral test. Oh, I didn't stop the share, sorry. That also, you could use the integral test on this because this is something that's integrable. But what I want to say is that this has a nice direct comparison. First, do the terms go to 0? Should have been asking that. Should have been asking that in all of these. The terms go to 0. Does n grow faster than natural log? Natural log goes slowly, grid n, so this ratio goes to 0. So it has a chance of converging. But now this is a little bit harder than that because it's not like, yeah, it's not like direct. It's not like something we can't just ignore the natural log over n of n. It does do something there. But I think it's kind of, if you just think about it for a moment, notice natural log of n is greater than 1 for n greater than e. So natural log of n over n is greater than 1 over n as soon as n is at least e. I guess it's not true for n equals 2, but again, finite terms don't matter. It's always the tail, the infinite tail that matters. So that means the sum is greater than the sum. And what happens to the right-hand side? This thing converges, right? Because the terms are going to 0. You should be, I'm being devious. That's the logic you shouldn't listen to. Terms are going to 0, so it converges. No, you said it's not true. What is it? It's p equals 1, right? So this diverges, which diverges. So this diverges too. So that's the thing. We know, I mean, just keep in mind that 1 over n, that series diverges. So be careful not to say 1 over n diverges because 1 over n doesn't, 1 over n goes to 0, but the series with 1 over n diverges. And so anything bigger than that will diverge automatically. Okay, so here I didn't sandwich between 2, but I did compare to something that, and I got the inequality on the correct side that I could make a conclusion. If this had been all, if these had all been less thans, if this had been a less than right here, then I couldn't actually conclude anything, right? Because this would be something that's less than something which goes to infinity. So it itself may go to infinity or it may not. Okay. Yeah. Let me talk about limit comparison, or maybe we should go and take a break for a few minutes. And then we can come back. You guys want to take a break for a few minutes? Yeah. The interest of the nods. Okay, let's take a break for a couple minutes. I'll resume. Okay. Let me just share screen for a minute too, but I will write this down. But this limit comparison test is a little bit weird. Although it ends up becoming, it's kind of natural. So you are comparing to you're taking a series that you don't know, and you're comparing it to a series that you know. That's kind of what we did in the direct comparisons, right? We compared to a series that we knew. But then you compute this ratio, which is the limit of the ratio of the terms. And you can sort of tell that that means that the two series, if you get something that's like a constant, there's an argument that the two series will behave the same. Let me go ahead and just start writing some of that on the board. So yeah, the other comparison test is the limit comparison test. And that says like, so we want to determine if some series converges or diverges. Say we judiciously choose the sum of Bn, whose behavior is known, like we know if it converges or diverges. And when we compute the limit of the ratio of the respective terms, we get some number C, which is not 0, not infinity. Okay, so it's like, yeah, we get some actual, I guess I'm saying all these series are positive series, so this is, we could say this is an actual positive number. Then, if that's true, then what limit comparison test says is then the sum of A sub n and the sum of B sub n either both converge or both diverge. So that it behaves the same. And the reason is, like, imagine C equals 3. Like, just to give you a sense of why we might believe this. Pretend C, this limit is 3. Right, just to pick a specific number for a moment, just to give us something to think about. Well, in that case, if then for n large, that means A sub n is approximately 3 times B sub n. Right? And then that means that the series is approximately 3 times this. I mean, again, it's not, maybe for the first million terms, this isn't a very good approximation, but for the rest, which is a lot more terms, it is true. And so therefore, like, if the second one is finite, it converges, then the first series also converges. And if the second one is infinite, it diverges, then the second series diverges, right? I guess this implies both converge or both diverge. Okay, so that's why this is sort of a useful test. Let me just say why. Why does this test work? And this is kind of my argument why this test works. Okay. And actually, one thing I like about this is it gives you a different way to do even that problem that's up on the top board on the left, or more complicated versions of it, rather than deal with like let me give you an example that's really complicated. Like, what if I just pick something that looks just terrible? Example. Sum of n to the 7th plus n to the 6th minus n to the 5th plus 73n minus 100 over, actually, let's put a coefficient here, 2, over 3 into the 8th minus 1,000 into the 4th plus 11 n cubed plus 14. Make this horrible. I don't quite know where to start this because I'm worried about crossing 0, but n equals something to infinity. Let's just say 1,000. That should definitely be, that 1,000 to the 8th should be bigger than all those. I probably can even get away with 100. Doesn't matter. Okay. That's not so important. I could even stick in like a natural log of, I can even stick in like a square root of n plus natural log of n, like this. Point is, those are all smaller. Those are all going to be negligible compared to the biggest thing on top and the biggest thing on the bottom, right? So what should this behave like? I mean, you should almost be able to tell me immediately whether this diverges or converges. It looks horrible, but if we think about what dominates the top and what dominates the bottom, yeah, why do you say diverge? Yeah, it's like into the 7th over into the 8th, which is like 1 over n. Okay, so this is our a sub n right here. This is our a sub n. But this should be like, you know, this is the dominant term on top is into the 7th, dominant term, just like Maggie said. So, and there's coefficients, but they don't matter that much. But so it should behave like 1 over n. So this is our b sub n. So this series should behave like the harmonic series. It should diverge. Let's actually check. So now we have to do the ratio. So compute the limit as n goes to infinity of a sub n over b sub n. Okay, well, makes the fact that I wrote something horrible makes it less pleasant. But we get this whole thing over 1 over n, which is really this whole thing times n, right? I'm so happy with myself. I've already made so many terms. But I'm getting a sense of just how this is like, you can take horrible things and make sense of them. Times n over 1, right? Dividing by 1 over n is the same thing as multiplying by n over 1. Flip. Okay, and now I could multiply through this n. And you do notice something if you multiply this n through. Sorry, I know this is sort of, I just picked a really terrible, oops. Forgot my limit, bad. So that's the limit. Okay, I'm multiplying everything through by n into the 8th, into the 7th, minus n to the 6th, plus 73n squared, minus n to the 3/2 plus n natural log of n. 3 into the 8th. The bottom doesn't change. Okay. But you should start to believe that like this is going to work out to be a nice limit, right? Right now it's infinity over infinity. What can I do? I did something very similar earlier in class. What did I do to the top and bottom? Instead of using L'Hopital's rule 8 times, to turn this, divide by, if I divide by n, that'll get me down in the 7th here. Divide by 1 over n. Well, I got to do the same thing to the top and bottom. So I want to make these infinities go away. So how can I make this infinity go away? What should I divide by? N to the 8th. It's the biggest power. It's the power that you see. So let's multiply the top and bottom by 1 over n to the 8th. I mean, you do see the power of this when we write this all out, because all the n's are going to be in denominators, which means we're going to be able to say that lots of things go to 0. Up here. Because I'm basically multiplying each of these by, I'm basically dividing every term by n to the 8th, right? So on top we get 2 plus 1 over n minus 1 over n squared into the 6th over n to the 8th plus 73 over n to the 6th why did I do these powers? Minus n minus 1 over n to the 13/2, I think, if you subtract 3/2 minus 16/2 plus natural log of n over n to the 7th, because I canceled an n there, all over 3 minus 1,000 over n to the 4th plus 11 over n to the 5th plus 14 over n to the 8th. Okay, this looks terrible, but like now it's nice, right? Because now as n gets large, we have all these fractions that go to 0. All of these. And in fact, even natural log over n to the 7th, we sort of said at some point that natural log grows slower than any power of n. We sort of justified that with L'Hopital's rule. All these terms, they all go to 0 as n gets large. So we just end up with the limit as n goes to infinity of 2 over 3, which is 2. Oh, that actually is the limit. Sorry. We just end up with 2/3, which is neither 0 nor infinity, which is kind of what the limit conversion test said, right? Neither 0 nor infinity. So this horrible series behaves like the harmonic series. So the sum of blah, I don't want to write it again, behaves like sum of 1 over n, which diverges. So this is somewhat nice. Maybe some definition of nice. But the point is whatever this horrible thing is, like we can analyze its behavior. Sort of just by looking at the maximum power on the top and bottom. Good. Okay, fun. I'm going to say the integral test quickly because we actually used it to justify the p-test. We did examples, so I'm not going to go too far into this. There is a video in the playlist that goes much more in depth. But basically, when we had like the series 1 over n, we compared it to the graph 1 over x and showed that the areas compared, right? Does that make sense? We show that the areas compared to each other. And so that basically the series behaved like the integral. And that's actually what we did for all the p-test ones. We said, oh, we can draw the series as an area, we can compare it to the improper integral area, and they behave the same. Therefore, it's all the same. So I'm just going to say that. I'm just going to state the integral test because it's the same idea. Now, there are some hypotheses you need. You need f of x to be positive and going down to 0. Do I not say that on the handout? Well, okay, it doesn't have to go to 0 because, right, it just has to be positive and decreasing because if it doesn't go to 0, the series is going to diverge, but so will the integral. So, yeah, so given the sum of a sub n equals 1 to infinity, I mean, this is always some function of n, right, a sub n. So, yeah, so a sub n is f of n for some function. Like, you know, there's some, like even that horrible one up there, we could just change the n's to x's and get some function f of x. Some function f of x. If f of x is, so this is the integral test, so we're comparing it to positive areas. If f of x is greater than 0 and f prime of x is less than 0, that's when I say it's decreasing. Because it has to be, it just turns out it has to be. Turns out if it can go back up, you can mess up and get weird little humps and you can break this thing. Again, I do an example of that in the video, but it's not that interesting. So really f decreasing. Then the sum, the series, and the integral either both diverge or both converge. Converge. Or both diverge. Okay, that's what the integral test says. The idea is that you just draw the series as an area and compare it. That's what we did for the p-test. All right, I'll just put that over here. The idea is draw series as an area and compare to the improper integral. And we were able to make, if you remember what we were doing last Wednesday, we were able to make it work sort of whether or not the areas were above or below, whether the curve was above or below the rectangles. We could like shift the rectangles a little bit. I'll give you an example that we've already done, but that also works with the integral test. This natural log of n over n example again. We can do this by a direct comparison. We did it by a direct comparison with 1 over n. But if you don't notice that, you might think, oh, well, I can integrate natural log of x over x. It's actually not that bad to integrate. So first off, check. So f of x is ln of x over x, which is greater than 0 for x greater than 1. It also decreases. You could do that just because natural log of x grows more slowly than x, so the bottom is growing faster than the top. Or you could literally compute the derivative and show it's negative. So I'm just saying, if you're gonna, you should give some argument. You know, if you're gonna do this on a test or something, you should be able to give some argument why it decreases. So compared to, so find, let's just find the integral of ln of x over x dx. It is funny that I switch n to x, but n seems to be like, in math, n seems to be used as a discrete variable for like integers, and x is used as a continuous variable. But how do we do this integral? All right, I'm going to do it the way that we're supposed to do it. As a limit, what can I can do this here probably. If I just had the indefinite integral, what can I do? Does anybody see? It's not anything as hard as by parts or anything like that. There's a substitution that works nicely. What's the substitution? Yeah. Yeah, if u equals ln of x, what's du? 1 over x, which is exactly in the integral. So this ends up being just the integral of u du, which is 1/2 u squared plus c. So it's just 1/2 natural log x squared plus c. So this is, the limit as b goes to infinity of 1/2 ln x squared from 1 to b, which turns out to be 1/2 ln b squared, because ln of 1 is 0. And that does go to infinity. Bless you. So both diverge. By the way, it's good that we found it diverges because we found this series diverge a different way. So we better get the same answer. So both the series and the integral diverge. Make sense? So that's the way the integral test works. That's sort of a last resort. I mean, most of the time, one of the other tests will work, but if you happen to find something that you can't figure out how to analyze it, and it turns out that the function that's in the series is something you can integrate, then that's fine. You can do it that way. I mostly it's used to just justify the p-test because we did the p-test for improper integrals directly by computation. Okay. Last 10 minutes, 10 to 15 minutes. Let's look at page two. Let's look at some of these practice questions. I'll share it for a minute with the. So one of the tests that we developed should apply to each of these. I mean, at least one of the tests. Let's just maybe talk through a bunch, maybe not doing the full details. Let's just see if we can try to guess a good test to use. Actually, let's start with, let's just do this kind of at your chairs, like just look at one, and if you figure that out, 2, 3 we did. Look at 1 and 2. Look at 1 first, and then try to compare notes to people around you and think of what test you would want to use and whether you think it converges or not. And if you get a good answer for that, you can look at number 2. And I'll write them on the board. The questions on the board so that people watching on Zoom can see which ones we're talking about. Some of these are kind of weird. People think they know what's going on with number 1. Yeah. It's, well, it's not directly of the form 1 over into the p's. So what do you mean? Oh, you're saying like you could break it up into 2 series. Is that what you're doing? Yeah, you're saying like this could be the sum of 1 over n to the 3/2 plus 5 over n to the 5/2. Like that. Is that what you're saying? The whole thing? Oh, because if you ignore the +5, you're saying? Yeah, so then that's the informal versus formal approach, right? Informally, you can ignore the +5, but formally, you need to do something a little more. But it's good. The informal thing is good because you can kind of guess immediately whether it's going to converge or diverge, right? You can guess it's going to converge. So that's one way. You could do this and just do some p-test stuff. These both, you could break this up into 2 series, both of which converge. You could say the +5 is negligible. But really, sort of, if you wanted to justify it, you either have to do this algebra, or you could probably do a direct comparison or a limit comparison. Direct or limit comparison. I think either of those would work. So this thing converges, right? I'm just gonna do that. What about number 2? Very similar. What's Maggie?
I mean, I did this similar thing where I found it more
Yeah, this is really the first thing you should check, which is, are the terms going to 0? Here, I guess you should check that too, but here the bottom power is bigger, so the terms are going to 0. Here, the terms aren't even going to 0, right? And you can see that sort of like Maggie said informally, or you can just see that like, or you can actually do the limit like we did with that other example. So this diverges. Okay. Rule 4 is a little trickier, actually. I sort of made them get tricky and different, and not in the right order. And we're going to actually learn a different technique for 4, but it's still worth thinking about. Are the terms going to 0? Which grows faster, 3 to the n or n to the 5th? Exponentials grow faster than polynomials. So we can't say that the terms don't go to 0. Let's see. So exponentials grow. And again, we can sort of justify this with like L'Hopital's rule or something. Like we could do L'Hopital's rule on this expression 5 times, then top would be constant and the bottom would still have a 3 to the n in it. So n to the 5th over 3 to the n goes to 0. So it's possible it could converge. Doesn't guarantee. Actually, look at number 5 though. What does the exact same argument tell us about number 5? What's happening to the terms as it gets large? Yeah, these are actually going to get bigger and bigger as it gets large. So you're actually going to be adding larger and larger numbers. So here, 3 to the n over n to the 5th goes to infinity. So this diverges by the test for divergence. So this one diverges. Okay, this one's interesting because there is this way we're going to learn to do this called the ratio test, but I actually think that there's something more intuitive, which is really that if exponentials grow faster than polynomials, then n to the 5th doesn't only grow more slowly than 3 to the n, it actually could go more slowly than 2 to the n. So we could actually use the same argument to say n to the 5th is less than 2 to the n. for n bigger than, I don't know, when does it happen? It doesn't happen for a while. Actually, it doesn't happen for a while because even 10 to the 5th is, so it's probably a while, but for n large enough, which means that n to the 5th, sorry, let me go down here where I have more room. N to the 5th over 3 to the n is less than 2 to the n over 3 to the n, right? That's a nice, it's just a nice thing to have in your tool bag that like, you can always compare, you can always use exponentials. I could even do like if I needed to, I could do 1.001 to the n here if I really wanted to. And that's 2/3 to the n. So the sum of n to the 5th over 3 to the n is less than the sum of 2/3 to the n. Again, for n large enough. But what kind of series is this? Has that nice name. It's geometric, right? And the r is 2/3, so it converges. Geometric, r equals 2/3, so it converges. And this converges, so this also converges because it's smaller. Okay, does that make sense? Again, there's another, you can hammer this with a more direct test called the ratio test, which we're going to learn. But I do like that you can give sort of a more, what I think is like an intuitive argument if you just believe that exponentials grow faster than polynomials. It also really means that we could put any power, we could have like into the millionth over 3 to the n, and that would still converge. It's harder to believe, but it's true. You have into the millionth over 1.001 to the n, and that would converge. All right, I think we'll stop there, but you might look at some of these. We'll keep going with some of these on Wednesday. And then we'll start talking about tests, series that aren't always just positive terms, which we have to think about a little differently. Okay, everyone, thank you. Take care of yourselves.